It is a great, really enormously great pleasure to introduce our distinguished key lecturer, Tom Mitchell. Tom visits with us from Carnegie Mellon University, where he is the Edward Fredkin. Yes, the person who invented the gate. So he's the Fredkin University professor at a department that he himself founded, the very first department of machine learning in the world. Here's a lesson to us doing multidisciplinary research. There are options beyond trying to fit in an existing department. You can start your own department, just like you can start your own institute. Tom was there for the very beginning of machine learning. He got his undergraduate degree in electrical engineering at MIT, starting his studies there the same year that Marvin Minsky published the book Perceptrons. Tom then got his PhD at Stanford, starting his studies there 10 years after Gene Golub published his algorithm for computing the singular value decomposition. Well, you see an eigenvalue decomposition which is stably computed via the SVD, or the singular value decomposition, is at the foundation of perceptrons. Those of us who are physicists know that the SVD is also at the foundation of the theoretical description of the physical world, so some of us think it may very well be the foundation of describing all natural phenomena, or even all phenomena recorded by data. Let's think about Google and Netflix. Well, I digress, and Tom will tell us that the SVD alone is not machine learning. So Tom was there at the very beginning and went on to define and develop machine learning in his research, mentoring, and service to society. Tom's research uses machine learning to develop computers that are learning to read the web, and uses brain imaging to study how the human brain understands what it reads. You see, if you want to teach a machine to do what the human brain does, you might want to understand how the human brain does that. And not to us teachers, maybe one day we will learn from the behavior of machines how to teach humans. Well, that didn't go well. Tom received many awards in recognition of his research. For example, he is a member of the US National Academy of Engineering and of the American Academy of Arts and Sciences, and a fellow and past president of the Association for the Advancement of Artificial Intelligence. His service to society includes co-chairing the 2017 US National Academy Study on Information Technology, Automation, and the US Workforce, and testifying to the US Congressional Research Service and the US House Subcommittee on Veterans Affairs regarding potential uses and impacts of artificial intelligence. In our big data time, machine learning is not just what we all do in our labs to make discoveries from data, but we hear also what venture capitalists are looking to invest in. And Tom, who has been involved in several startups over the years, including, I learned today, one with offices here in Provo, is a sought-after presenter at venues such as the World Economic Forum. So, just to finish, it seems the song by Drake may apply. Definitely this line, started from the bottom, well, at MIT and Stanford, now we're here. Maybe also this line, on the road, $500,000 for a show. I should note that Tom's visit with us is pro bono, and we're so excited that he's here. Everyone, please help me welcome Tom Mitchell.
I don't think I can follow that. That's great. Thank you, Orly, for the very kind introduction. And it's great to be here at SCI, especially since Chris this morning told me I have to pronounce it ski. And what I'd like to do today is talk about a thread of research that I've been involved in for the last more than 10 years. But it really centers around a very simple question, which is, how does neural activity, well, two questions, encode word meanings, and how does the brain combine those word meanings into sentence and beyond? So how does the brain understand language? I'll tip my answer is I don't know how the brain understands language, but we have been studying this. We have some symptoms of how the brain understands language that I want to share with you. And so in a nutshell, this talk is really a discussion of how we might pursue these kinds of questions through a combination of brain imaging studies and machine learning methods for analyzing that data. So I want to start by pointing out that most of the work that I'm going to describe is actually done by other people, including some wonderful graduate students I've worked with, and Marcel Just, who taught me how to use fMRI imaging a number of years ago, and who's still one of my favorite collaborators of all time. So suppose you're interested in the question of how the brain represents meaning with neural activity and how it processes language. And you have access to brain imaging devices like an fMRI scanner. Then you might begin, as we did, with putting people in the scanner and showing them stimuli like this. So maybe sometimes we show them words, sometimes we show them pictures, sometimes we show them pictures with words, but in any of these cases, we're just trying to get them to think about some concept and then see what happens inside when they do that. And so, for example, here's a part of a three-dimensional image. Looks like 4 images, but it's 4 slices out of about 25 of an fMRI image when this subject looked at this stimulus here, bottle. And to help you decode it, here's a thermometer, but the top of the picture here is the back of the head, and the bottom of the picture is the front of the head. So that's what the brain activity looks like if we show a particular person this stimulus. And so you're probably thinking, does it look any different if I show them a different word? Let me show you what activity we get on average if we show 60 different stimuli, and that looks like this. So you can see bottle looks a lot like your average word in terms of neural activity, but it's slightly different. And if I subtract out this mean activity from the activity for bottle, you can see more easily what the difference is, and there are some differences. Some of those differences are noise, some of those are signal, repeatable, but that's the kind of data we're working with. Okay, so the very first thing you might think, especially if you are interested in machine learning, is there enough signal there in the fMRI data to distinguish different words? And we can turn that into the equivalent machine learning question, which is, can we train a classifier so that when it is given a brain image, can it distinguish between which of the stimuli words the person was thinking about when we took that image? And so we've trained a variety of different kinds of classifiers, logistic regressions, deep nets, support vector machines. And the answer is that yes, there is enough signal in the fMRI data to distinguish different words. And here you see for different participants in one of our early studies, the accuracy with which the classifier can decode which of 2 classes of words the person was looking at. And of course, this is tested on a set of images which were not part of the training set. So in this case, the subject was either looking at words about tools, hammer, screwdriver, pliers, or buildings like palace, house, garage. And you can see that for many of these subjects, for all of these subjects, the accuracy of the classifier is better than the chance accuracy of 0.5. Okay, so this is good. This means, yes, there is enough data in fMRI to see there's enough resolution, even though 1 cubic millimeter of neural tissue, which is about the maximum resolution we can get from fMRI. still contains 50,000 neurons. So we're kind of fortunate that brains are organized in this way that we don't have just a grandmother cell and a single cell for each concept. Otherwise, I wouldn't be giving this talk. But fortunately, brains are organized in this more blurred out kinds of patterns of neural activity. And so, in fact, we can see distinctions. Okay, now once you get that idea, we can start using these trained classifiers. The way I think of them is that they're virtual sensors of information content. So just like fMRI was one revolution because for the first time it let us look inside the head of people without taking their skull off and see the neural activity. That was a revolution. But now I think of these classifiers as trained virtual sensors, not of neural activity, but of the information encoded in that neural activity. And you can boutique design your own classifiers, for example, to distinguish which word somebody's reading or lots of other things. So it's another tool that gives us the ability now not just to look at activity, but to look at information content. And I have to say, this morning as I was listening to some of the work going on here at SCI, I was wondering if in other biological domains there might be an opportunity to go beyond looking at biological activity and think of characterizing it in terms of information content. Like, could you train a classifier to tell when a cell was at the processing stage that it's ready to subdivide or something like that? But you're the experts on that, not me. I shouldn't go there. So back to the main storyline. Once we have this idea that we can train classifiers, we can ask a number of interesting questions. Like, is your pattern of neural activity that encodes different words the same as mine? And we can do that by turning it into the corresponding machine learning question. Can we train a classifier using data from your brain and then successfully use that to decode which word I'm thinking about? And if the answer is yes, then obviously that's very compelling evidence that we have very similar neural codes. Or maybe that's not the way it is. And we didn't really know when we began this research, so we ran that experiment. And the answer is absolutely yes. We do have very similar neural codes. So here you see, again in black, the accuracy for decoding this is the rank accuracy for decoding which of 60 items somebody's thinking about. And in black, you see the accuracy if we train on data from the same person that we're later testing on. But you see in white, the accuracy that we get if we never use data from participant 7, but instead we only train on data from everybody else. And then we test on participant 7. And you see on average, these are about as accurate. It doesn't really matter whether we trained on the person we're testing on or everybody else. So this was, to me, really a remarkable result because even though we all have very different backgrounds, and we think we're all different, and we are all different, there's something biologically that results in us having at least spatially distributed patterns of neural activity that are very similar for coding word meanings. At least concrete nouns. These were concrete nouns means just nouns that refer to things you could touch, like hammer, house, so forth. Okay, we can ask the same question. Not only are neural representations similar across people, we could ask, are they similar across language? We got bilingual Portuguese-English people. We trained by showing them the words in Portuguese, and then we tested on the same person showing them instead words in English. And again, we found it really didn't matter. What are the implications of that? Well, what that means is that the patterns of neural activity that the program is discovering really are not about the surface level percepts, Portuguese or English. They really are the patterns of neural activity about the meaning of those words, because that's invariant across languages. We could ask the same thing, what if we show you words and then train on words and test on activity when we show you a picture? And again, we found it really doesn't matter. So it really doesn't matter how we get you to think about a hammer, it's that pattern of neural activity. Yes?
Are you able to classify if it's a word?
Yes, we are able to classify whether it's a word or a picture. That one is actually fairly easy, a high accuracy classification, because the brain activity is quite different. On the other hand, we found things that were, we tried some things which were easy and some that turned out to be hard. I thought it was going to be hard to get reliable patterns of neural activity for emotions like anxiety, love, hate, sadness. But in fact, they are just as easily classified as concrete nouns. On the other hand, verbs turned out to be almost impossible to classify. So we could not tell, for example, the difference between whether you were reading the verb heal or the verb cut. We couldn't even, within a single person, could not train a reliable classifier. But we later found out that we could classify whether you're reading the two-word phrase, surgeons heal and surgeons cut. Even though we couldn't tell the verbs apart from neural activity when presented in isolation, once we gave them a subject, surgeons heal, surgeons cut, then we could decode it just as easily, just as accurately as these things. So there's something special about verbs, that the pattern of neural activity your brain represents is somehow stable when you give it a subject, but in the abstract, or in isolation, maybe it's just too abstract. And it kind of makes sense. If you think about a verb like enter, enter has many meanings, actually. It's a pretty abstract notion. You could be entering the room. You could be entering a contest. You could be entering the freshman class. There are a lot of different notions that could mean, but once you ground it, it has a well-defined semantics. Okay, so that's all I really wanted to say about classifiers, but the key lesson there is, in terms of machine learning, think of training these classifiers corresponds to building yourself a virtual sensor of information content in the image that you're looking at. Yes?
So when you have misclassifications in the across populations, similar for different participants?
Confusion meaning, oh, you mean words that are... Yeah. Yeah, great question. The question, if you didn't hear it, was across different people, are the confusions between different words in terms of the classifier's ability similar? Absolutely, yes. And in fact, we later found out that there's a very strong correlation between the corpus statistics of two words and how similar their brain images are. So if you actually look at the cosine distance between two fMRI images, if you treat the image as a vector, that cosine distance correlates very strongly with the corpus statistic, the cosine distance in corpus statistics for the two words. So the more similar they are semantically, the more confusable they are in terms of neural activity. I'm going to move ahead and try to leave some time for questions at the end. I love questions, but I know you hate overlong talks, so it's a balancing act. Okay, so now that we have the idea of classifiers, that's nice, but it's not really anything close to a theory of how the brain represents things. Theories, of course, are logical systems that make predictions about phenomena that we haven't yet maybe collected data for, and then we can test those theories. So what would it mean to have a theory of neural codings in the brain? Well, part of it would certainly be the ability to take an arbitrary noun as input and then predict what would be the neural code for that noun. And so we got interested in this question and ended up being able to build a model that did this not perfectly, but considerably better than chance. And the first version of the model looks like this. Given an arbitrary noun, it predicts the pattern of neural activity in a two-step process. The first is it looks up on the web, in a trillion words of text on the web, some corpus statistics about the use of that, the appearances of that word in the text. In the first model, that resulted in a vector embedding, we would say today, or a vector encoding of telephone in terms of how frequently that noun occurs with 25 different verbs, like run, eat, taste, smell, touch, and others. And so this gives us a canonical representation, a vector encoding of arbitrary nouns. And then in the second stage, that vector was used to predict the neural activity at 20,000 different locations in the brain as a linear function. And so let me just show you a little bit more detail about that. For example, if we look at the noun celery, the corpus statistics look like this. It occurs a lot with the verb eat, but not very much with the verb ride. And then airplane occurs a lot with the verb ride, but not very much with manipulate. So these corpus statistics that we collected for 25 verbs was the representation that the model used. And then based on those vectors, we trained the second part of the model, which would predict the neural activity at any given location as a weighted linear combination of those vector features. So now that we know celery occurs 0.84 with the verb eat, the question is, how does that feature of celery contribute activity to the neural code? And so in the end, the predicted activity at vector at voxel v is just the weighted linear combination of how frequently that input word celery occurs with the ith verb, eat, times some learned coefficient that tells how much that ith verb contributes to the vth voxel. And so it gives us about 500,000 parameters here, and these are actually images of the learned parameter values. These are not images of fMRI data. These are the coefficients that were learned according to the model. To the degree that a noun occurs with the verb eat, it's going to add in this subpattern of spatial pattern of neural activity. Okay, so it's a linear model. And in the end, you could ask, does this model work? Well, I can show you when we train on words not including celery or airplane, so the program has never seen these words, it predicts these patterns of neural activity, whereas we actually observe these. So you can see it's not perfect, but it's capturing some significant activity that actually does appear in the observed images. And you can also ask more quantitatively whether it works. What I could do is I could give this program to test it quantitatively. I could give it the word celery and airplane and say, predict the images. Then I could show it these two, but not tell it which one is celery and which one is airplane. And it would have to tell me. And at chance, it would be right 50% of the time. And in fact, what we found is this right 79% of the time. So what that means is 3 times out of 4, once this model is trained, we can give it, if we give it 2 words it has never seen and the corresponding 2 brain images, then 3 times out of 4 it can tell us which of those 2 new words goes with which of these 2 new brain images. Okay, so that's a kind of quantitative measure showing that the model's not perfect, but it is capturing something systematic about your neural code, which is really, again, a remarkable thing. It could have been, if I was designing a brain, I wouldn't be that good. I might come up with the idea of hash codes for words. Well, that's not what's going on. There's a systematicity. The fact that this works means that there is a systematicity in the way that these different neural codes for different words work. In fact, if you think carefully about what this model is assuming, what it's assuming is that any word you can think of lives in a 25-dimensional space. That's what those 25 verbs were. And the co-occurrence frequencies with those 25 verbs are the coordinates in that 25-dimensional space. So this model is essentially assuming that every pattern of neural activity for any word you can think of is this weighted linear combination of 25 more primitive subpatterns of neural activity that correspond to a basis set in that semantic space. So that's kind of interesting. Now, do we have the right basis set? That was the next question we got to, is could it possibly be that we were right when we guessed those 25 verbs? I'm sure the answer is no. But it's interesting to remember that there are a lot of different 25-dimensional vectors, basis sets that span the same space. And so all we need is one of those to span the space. And it just means we're characterizing a good space. It doesn't mean that we have the exact basis set the brain is using. In fact, if you think carefully, it's not even clear that's a well-defined question to ask what is the basis set the brain is using. You might have to refine that question a little to make it well-defined. Okay, but anyway, we started looking at different feature sets for this. Use more verbs or use the 50,000 most frequent words in English and so forth. And we tried things which did not work, but then we got something that worked better. And that's due to Dean Pomerleau, who was a robotics professor at CMU, and was working with us. And he came in one day and said, here are 218 features. They're like the ones you would use if you played 20 questions. Can it break? Can it swim? Can it change shape? Can you sit on it? And he had gone on to Mechanical Turk, Amazon's Mechanical Turk service, and collected answers to these 218 questions for each of our words. And so now we have, instead of the 25-dimensional verb features, we have these. And this did work better. But then the best solution we found worked even better and used only 20 features. I see Orly smiling already because she knows the punchline on this one. And this one worked better, and I'm proud to say we turned it over to a machine learning algorithm. And this is the PhD work of Indra Rustandi. What he did was he used a technique called canonical correlation analysis, where in this case, instead of training the model on data from just one person, which is what we had been doing, he took 20 different data sets where people had seen the same 60 stimuli. In some of these data sets, they saw the word only, and others they saw word plus picture, but it was the same 60 stimuli. So we have 20 data sets, and he learned a 20-dimensional latent representation using CCA. That means what CCA is doing is it's learning a linear mapping from the images of each subject, a different linear mapping for each subject from the image to this 20-dimensional space. And I'm sure this is like generalized SVD. In fact, what canonical correlation analysis is really doing is given two matrices of data. imagine that each column here is one fMRI image. And here's fMRI images for the same 5 stimuli, but from a different person. Then it's learning 2 linear mappings, 2 vectors, such that Wx and Wy, such that if we multiply this matrix by that vector, we get a set of 5 values that correlate highly with the 5 we get if we multiply this instead. So it's called canonical correlation analysis because it's solving for these linear functions, linear mappings, such that they maximize the correlation in the projected space. So it's a way of learning a latent representation that's shared across these different data sets. And so we did that to learn the latent representation, but now we want a model that will predict the brain activity. So he trained a second part of the model which takes the word and encodes it in terms of those 218 can you sit on it type of questions, and then train the model to predict, again as a linear function, the values of these 20 latent features, and then inverted the linear, did a pseudo-inverse on the linear functions we had here. So now we have a forward model that again starts with an arbitrary word, predicts in a subject-independent way what the 20 components of neural activity will be, and then can project in a subject-specific way what the actual brain image produced by those 20 components will look like. So I like this model a lot because it works well, but also because it does something that we need to do more of, which is build models that have a subject-independent component that captures what's the structure that's shared across the population, plus a subject-specific set of parameters that are learned separately that capture the individual variations. So this, and in fact, at this point, this is still the most accurate model that we have on this data set. So I want to skip over that. All right, so that's, to summarize then, what we've seen is that from fMRI, there's enough resolution in the neural activity that we can see, that we can distinguish thinking about different words. And furthermore, there's systematicity that's shared across all of us in terms of what are the more primitive components of neural activity out of which the semantics of entire words are built. And in fact, we have a model that, when trained, captures to some degree that systematicity. So that's forward progress. It's not there are plenty of open questions. But one of the open questions really has to do with timing. One of the unfortunate things about fMRI is that you get an image about once a second. And do you know how long it takes you to understand a word? If I put a word up on the screen, it's about 400 milliseconds. So that's way too fast for us to see anything about what's really happening if we're using 1 second frame rate fMRI. So we went off and studied a second neuroimaging method called magnetoencephalography, MEG imaging, which has the advantage that we get an image once per second. Millisecond. We get 1,000 images per second. So now we can make a movie of what's going on during the 400 milliseconds after the word appears on the screen to see what's going on up there. And here's a movie I'll show you where this person is looking at the stimulus hand. It's a word and a picture. The movie begins at 20 milliseconds before the word appears on the screen. Don't watch the clock because you'll miss the good part of the movie. But I'll play the movie and I will just read out when it gets to 100 milliseconds. So you watch the movie. So here's what happens. words on the screen. 100 milliseconds. 200. 300. 400. 500. Okay, so you get the idea. There's a lot of dynamics here. It's not just like a static fMRI image. There's a big temporal component to what's going on. So now the next question is, how can we make sense out of this? And let's go back to the first part of the talk where we said fMRI is great, so is MEG, because they let us see neural activity. But we really are interested in what's the information encoded over time in that movie. I want a movie not of neural activity. I want a movie of information flow. I'm a computer scientist. And that's also the way I want to try to understand the brain. So what's the information processing? So Gus Sudre, one of our PhD students, there's Gus, for his thesis made such a movie. What he did was he went back to training classifiers. He said, let's train 1 million classifiers, and he did. Each classifier would look at one brain region. We had 70 anatomically defined regions of the brain. It would look at a 50 millisecond snippet of that movie, and it would try to, based on that input neural activity, 50 milliseconds in one region of the brain, try to predict one of those 218 features that codes word meaning, like can you sit on it? And he trained those classifiers, and he tested them on held out data. And there were about 1 million, and most of them didn't work, which of course should not be a surprise, because most of the places in your brain at any particular 50 millisecond time window are not encoding a particular feature that you picked in advance. But some of them did work. And so then he made a movie out of showing the pieces of information that could be encoded in the 50 millisecond slice. And that movie looks like, this is a crude version of the movie, but in the first 50 milliseconds after the word appears on the screen, nothing could be decoded from that brain activity. The next, but at 100, it's possible to decode really perceptual features of the word, like how many letters, the word length, how many letters are in the word, but nothing semantic. At 150, same deal. Around 200, we see our first semantic feature, is it hairy? Which I think is actually a placeholder for is it animate, but we can get to that. At 250, we start seeing more, 300, 350, 400. This is, by the way, 400 milliseconds is post-stimulus onset, is the time at which we see a very easy to spot surprise signal in your brain if I give you a word you weren't expecting. So if I tell you the sentence, I drove my car into the refrigerator, 400 milliseconds in, after you see refrigerator, your brain puts up a big surprise signal, which is one piece of evidence that led me to say it took you 400 milliseconds to understand the word. But it also happens to correspond to when we can decode from the neural activity the peak decoding accuracy of what the word was. Okay, so it goes up and down. So that's what Gus's movie looks like. Now, the full set of data is 218 features. It's complicated. But I want to show you, I want to go down in one detail in this, which I think is really interesting. Let's just pick one feature, but it's representative of what we see for many of the features. And I could show you, we could ask the question, I'll pick the feature number of letters in the word. That's actually the first feature that can be decoded. And I'm going to show you a plot where it'll be a matrix, but each column will be a different one of those 70 regions of the brain. And each row will be a different 50 millisecond time window. And the color at that XY location is how accurately can we decode from that brain region at this 50 millisecond time the number of letters in the word. And I want you to think about what you don't yet know about the answer to that question. Like, it's just in one place and then it spreads to other places. Once it's encoded in one place, does it persist for a while or does it just go away? What is the flow? What's the information flow look like? And it looks like this. Here's a plot. So these are different brain regions. This is time. This is the color indicates the decodability of the number of letters in the word. And you can see that what actually happens is there are half a dozen different locations in your brain. Many of them are bilateral. This is left and right lateral occipital, for example, and left and right lingual. But half a dozen bilateral regions of the brain, which simultaneously, at about 100 milliseconds, contain neural activity that we can use to decode the number of letters in the word. And then they keep that for maybe 100 or 150 milliseconds, and then it's gone. By the time we get to 400 milliseconds, when all those semantic features are sort of at their peak, you can't even decode anymore how many letters were in the word. So I find this pretty interesting. I didn't expect this. And it leads to all kinds of questions like, are these different regions collaborating, or are they just happen to all get it at the same time, independently compute some features of the word? And so more recently, our student Maria Teneva, who's writing up this result now, she did the following thing. She said, well, let's look at those different regions that encode neural activity. The one that encodes it most strongly, that we can decode most accurately, is lateral occipital cortex. It's one region. And so what she did was she looked at the question of the functional connectivity, the synchronicity in the neural activity of lateral occipital cortex, the region where we can decode word length best. She looked at how correlated is that neural activity, temporally correlated, with these other regions in the brain. And the idea is that if they're temporally correlated, some people will use the term functionally connected, then that means they must be communicating in some way, otherwise it would be unlikely that they would coincidentally be temporally coordinated. And so what she found was that the neural activity in left lateral occipital cortex significantly correlates with the other regions that encode word length. And furthermore, if you look across the other 69 brain regions, you see that the degree of correlation in the degree of synchronicity between lateral occipital and these other regions is very well predicted by how well this other region encodes word length. So indeed, these different regions that encode word length are coordinating. And furthermore, if you look at the time from stimulus onset when that synchronicity, that functional connectivity peaks, each color here is a different person in our study, a different subject in our study. It always peaks 25 to 100 milliseconds before you can suddenly decode from the neural activity that word length feature. So not only are they synchronized, but they're synchronizing prior to the point where the information is actually encoded simultaneously across those regions. So this leads to a hypothesis that indeed they are working together to get this feature. Their functional connectivity synchronization peaks actually before the time when their local neural activity encodes the feature. And so Maria is planning to do some more work on this, and so this is hot off our presses. Okay, so I'm going to skip a slide. I had my eye on the clock. So far we've looked at, with fMRI, single word spatial distribution of neural activity. With MEG, we could look at then the timing on that. We see that we have the beginnings of a kind of information flow diagram in the brain of what features are coded and how they unfold over time. But most of language is really about not one word. That's why this talk is taking so long. It's about many words. So we have some newer work. For example, Nicole Rafidi, another of our PhD students, is looking at sentence reading. And if you're a subject in her experiment, pay close attention. This is what you will see on the screen when you're in her experiment. Okay, so we present one word at a time for 500 milliseconds each. And you get pretty used to reading this way. It's not exactly natural, but it's pretty rapid serial visual presentation. It has its own acronym, RSVP, so it's widely used. And if you record the MEG activity, this is what you see. And now, in this case, the horizontal axis is time. The vertical axis are the 300s. Each column is one MEG image turned into 306 sensor readings. That's what the MEG helmet actually gives us as raw data. And so what's remarkable here is you can see, even I drew these green lines in. Those are my green lines just to tell you where the boundaries are when the next word came on the screen. But even if I didn't draw those green lines, you could probably tell me where the word onsets were in that 5-word sentence. Furthermore, look at this. We never expected this. After the last word, there's an explosion of neural activity in the brain. Bigger, actually, than we see during reading itself. So this opens up the possibility of starting to ask, what's going on in sentence processing? For example, which of these words that you've already seen, when we get, let's hear, the student found, when we get to this point, and we look at the neural activity at that point, does that neural activity encode any of those previous words? Or just the word we're looking at? And by the way, what's coded over here? Any of the identities of those earlier words? And so Nicole's thesis, which is ongoing, is to look at those kind of questions by, again, training classifiers analogous to what Gus did when he made that movie of single word information flow that we just looked at. But now we can ask it at the sentence parsing level. You can ask, which words are you thinking about when? And I just want to show you one of two of our results. One is we found that in this study we presented a number of sentences, but they were always sentences of the same 5-word length, and they were all of the form the noun, verb, the noun. So the student found the hammer, the dog ate the bone, active voice sentences with 5 words like that. And we found that with that data set, we could decode what the verb is while you're reading the verb from this neural activity. But we could also decode from this neural activity what the verb was after you've read it. Furthermore, we could also decode here what the first noun was, and we could also decode here what the second noun is. So my hypothesis is that this is where you're thinking about the proposition itself, right? The proposition is there's some finding activity going on, and the student is doing the finding, and the hammer is the thing being found. You've got to semantically build this representation in your brain out of those words. And we find that, indeed, we can decode the verb and the 2 nouns here. Sadly, we cannot decode which of those nouns is argument 1 versus argument 2. We can't tell whether the hammer found the student, or the student found the hammer, or whether Mary kicked Bill or Bill kicked Mary. So we don't know who did what to whom, but we know who the players were and we know what the action is. And so this is kind of an open question at this point. Yes? I'm sorry, say again? That's right. So it could be the brain is, right, trying to simulate, or who knows, right? Somehow it's cogitating about the meaning of the sentence. And one question is, at what point does the meaning actually get built? I mean, you can't, when you see the student found, you can maybe build part of the proposition, but you can't really build the whole proposition until you get to hammer. So possibly this is where it's building it and thinking about it, and we really don't know. But we do know that your neural activity actively encodes those three, the verb and the two nouns at this point. Now, interestingly, we also found most of the words cannot be decoded before this point. That is, if I look here, when you're reading the word hammer, we cannot decode from this neural activity what the verb was. We can decode it here, but we cannot decode it here. Now, obviously, your brain has a short-term memory, and you're remembering the words in the sentence, otherwise you couldn't encode it here. But to me, what it looks like is happening is this. There's some mechanism in your brain that's doing short-term memory that's not burning very much neural activity. And then when you get to this point, you start burning a lot of neural activity to represent, and I believe, do inference around what those nouns and verb are. And so one hypothesis could be that your brain has a low energy way of storing in the short term the words that are in the sentence. And when the neural activity that we're seeing perhaps is mainly the neural activity associated with thinking about or drawing inferences or reasoning about those components. Like, is a hammer really something that could do finding? No. Could a student? Yes, students can find stuff. Hammers can't. Doesn't make sense, right? So, but somewhere in your brain, you need to look at those constraints and the syntax of the sentence and put together what you believe is the meaning of the sentence. And so current best hypothesis, which could well be wrong, is that the neural activity we're seeing is actually mostly associated with doing inference, that kind of constraint checking and other kinds of inference, whereas there's another mechanism that is so efficient that we can't see it above the noise in the MEG signal, a short-term memory mechanism that's keeping track of what the words in the sentence actually are. But anyway, that's the experimental evidence we have. So instead of talking for another 2 hours, what I want to do is end here, because I really want to have time for a discussion. And so let me just verbally cover a few other things to give you an idea of where we're trying to go from here. So we've been pushing recently more on the multi-word processing of language, like sentences. Recently we had a wonderful PhD student, Layla Webby, complete a thesis where she had people read in the same way, one word every half second, Harry Potter stories in the scanner. And she built a model to predict, just like the first model for predicting the fMRI images from a word, where we would get a word embedding vector. Telephone gives you this vector representation, and then we could predict the neural activity. In her studies, she built such a vector, but out of all kinds of features. She had hundreds of features in her vector that correspond to range from things like perceptual features, how many letters are in the word, to semantics, what are the verbs that co-occur with a word and so forth, to story level features, like, is there a conversation going on right now in this story? What's the emotion being experienced by the character we're focused on right now? Is this the first time, that we've met this character? Is there a physical action going on in the story? And things like that. But it was the same machine learning idea of building a vector representation of the information that we would subjectively think is included at that point in the story, and then looking for evidence of that being encoded in neural activity. And indeed, she found results that showed, for example, a very strong signal differentiating between when two characters were talking to each other versus just single character stuff that you're reading about, for example. So we're trying to push in that direction. And then the final thing I want to mention is a new project that just started up about a year ago with a neurosurgeon at University of Pittsburgh Medical Center who does deep brain stimulation on people with tremors, Parkinson's patients. And as part of the deep brain stimulation procedure, the patient is awake. And so on the probe that's being used to stimulate, we can also record local field potentials, and from that try to decode individual neural firing in the local region where the probe is. And at the same time, the patient has a ECOG grid, a small grid of electrical sensors directly on the cortex, over left temporal and motor strip kind of regions. And while the patient is awake, they're listening to a recording that says, please say the sounds ba, va, goo. And then the patient says ba, va, goo. This gives us data, acoustic data, their sound, the neural activity from the ECOG grid, and the direct local field potentials where the stimulation is occurring, so that we get a different collection of types of data. The purpose of this study, which is funded by NIH, is actually to study a clinical issue, which is that a side effect of deep brain stimulation is that it can interfere with word articulation. And so the point of this study is to try to understand what's going on, in what cases will it and won't it interfere with word articulation, what is the role of the subthalamic nucleus anyway, which is the region we're stimulating. And so that's the clinical side of it. But as a side effect, we're getting new kinds of data that are very local, not the kind of global imaging stuff we see. But I think that hopefully can complement what we can see from there. So, to distill this talk into, okay, 2 sentences. Here's what what I hope you get out of the talk. Number 1, you're more alike than you think in terms of your neural encodings of meaning. And number 2, given that the brain is an information processor, and perhaps a lot of biological systems can be viewed as information processors if we squint the right way, but because it is, these kinds of techniques that use machine learning algorithms to map from meanings, information content, to the raw data that we're getting in our images are actually the bridge that we need if we're going to try to build information processing models of biological systems like the brain. Okay, so let me end there, and thank you for your patience. And I'd love to, we have some time for questions. 'Cause I did that.